Okay, so now we're going to look at the chain rule. By now, you're getting really good at differentiating all kinds of different functions. You can definitely do polynomial functions like this one, x cubed plus 2x minus 3. You'll have no problem. We've learned how to do trig functions. We've learned how to differentiate log functions and exponential functions. But now we're gonna really kind of broadly expand your horizons in terms of the types of functions you can differentiate by using this rule. Now let's like this function here. You definitely know how to differentiate this x cubed plus 2x minus 3. You could do it in a matter of seconds. And this other function here, g of x equals the square root of x, you can also do really quickly. You'd probably want to rewrite it as x to the 1/2 power and then apply the power rule. But you can do it quite easily. But how would you go about differentiating the composite of the two? F of g of x equals the square root of x cubed plus 2x minus 3. I mean, you can do each individual bit, but what if you compose them together? So we've got a rule for this called the rule for computing the derivative of composite functions. Like a function inside of a function is called the chain rule. Okay. So I want to take a few minutes and just try to explain how the chain rule works and why it works. This is a pretty good illustration that I've found. But before we get into that, I want to remember really at its core what is a derivative. And I've asked you this question in almost every lesson, and you've told me it's a slope or a gradient, and you're definitely right. But I want to define it this way: a derivative at its core is it's the rate of change of one variable with respect to the rate of change of another. So if we think in terms of slope or gradient, we would say that it's change in y over change in x. It's the change of one variable with respect to the change of another. We observe the change in one and then observe how that affects the change in the other variable. But what if changing x doesn't cause y to change directly? In other words, what if changing x caused a change in some other variable? We're going to call it u, and then that variable in turn caused y to change. So let's look at this example to find out. So imagine here we've got two fulcrums, F1 and F2, and they've got levers on top of them. The lengths of the levers are different depending on the side of the fulcrum, but we want to consider two variables. Let's start over here on the left-hand side. We've got this point x, which is at the left end point of the lever on fulcrum 2, and we're going to define our variable x right here to be the height of that end point of the lever above the ground. And then if we go all the way to the other end, here we've got point y, which is at the end point of the lever on fulcrum 1. And we're going to define our y variable to be the height of the end of that lever above the ground. So let's, if we imagine these levers pivoting about a fulcrum, we know they're going to kind of move in circular fashion. So if we were to raise this lever, if we were to raise y, it would move kind of like this. So that means our lever would now be up at an angle like that. Yeah, and our y variable would now be the height of that endpoint of the lever above the ground. Okay, so that's how that would work. it's our y is going to move horizontally a little bit, but we're really only interested in the vertical height of that endpoint above the ground. So I'll just erase that now that you get it. Okay, so let's imagine that we do move this endpoint y down here. Imagine that we move it so that the change in y is 3. In other words, point y is going to move 3 units, meters, I guess we're talking about, closer to the ground. So let's imagine it swings, oops, get my pen. So it's going to move down in this way. So now the lever looks something like this, and this is going to look something like that. So it's gone down. We would say that it's gone down this far. That's our change in y, our dy, and we're going to say that that's 3 meters. It's gone down by 3 meters. So this change in y, because it's a lever that's connected to this other endpoint, it's going to change the position of u. It's going to go up, but not as far, because the length of this lever is 6 meters, while the length of this is only 2 meters. So we could say that the length of this is 3 times as long, which means that a change that happens over here is going to be 3 times as big as the change that happens over here. So if this has changed by 3 meters, well, this change in the height of u, it's only going to go, this height is here, it's only going to have changed, there's our du, our change in u, well, it was only a third of what dy was, which is 1 meter. Okay? Now, I want to talk about this. I didn't explain this before. U and U dash, we're going to imagine that these 2 points are connected by a segment. And this segment is always going to remain horizontal, parallel to the ground. Now, it can shrink or it can stretch. And as this swings up here, well, we are going to have our little segment is going to go like that. It's going to stretch out because as this swings up this way, this would swing up this way. And that will be our new U dash, and there's our U, capital U for the point. But it's this segment connecting them is always going to, it is stretched, but it's always going to remain parallel to the ground, which means that U and U dash will always be the same height above the ground. So this is this, it has changed. The height has changed the same as this U. So this is also du, which is 1 meter. This right here. Okay? So, well, we caused a change in y of 3 meters, which caused this change in u of 1 meter. Now we need to think, all right, well, how has that affected x? Well, if we imagine our lever, I'm going to have to draw through this. Maybe I'll use a different color now. Our lever now is going to look like this. It's going to go here, something like that. So this part of the lever is 4 meters, while this part on the left-hand side is only 2. So this is twice as long as this, which means any change over here is only going to cause half as much of a change over here. So we could say that this little change, that's our change in x. It's gone down. Our x has changed. We could say that our dx is really only 1/2 meter. If this has gone 1 meter, well, that's twice as long, so half of that, that's half a meter change in x. So we can scroll down here. We didn't write this in before, but our dy du, the change in y with respect to the change in u, the change in y over here we saw was 3. So this was 3 meters, while du only changed 1 meter. So, and this looks quite a lot like our notation for a derivative. So the change in y with respect to change in u is 3. Now, what we just talked about was that same change in U caused a change in X. That change in U was still 1 meter, but it caused a change in X of only 1/2 meter. So we could say that the change in U with respect to X is 1 over 1/2, which is 2. Now, let's imagine that intermediate variable U just wasn't there at all. So we saw that as Y changed 3 meters, X changed by 1/2 meter. If we were to double that, we could say that if the change in Y was 6 meters, well, this change in X would be double 1/2 meter, or 1 meter. So we could say, going down here, we could say that the change in Y, if it changed 6 meters, the change in X is going to be 1 meter. So the change in Y with respect to the change in X is 6. Now notice, that's the same. Our change in Y with respect to the change in X, it's equal to the product of the rates of change of dy to du and du to dx, right? We saw that the rate of change of dy to du was 3. And then du dx we saw was 2. And it's exactly the same as the product of those. So it appears to be that the change of y with respect to x is the product of the change of y with respect to u and the change of u with respect to x. And that's the main idea behind the chain rule. And hopefully that'll help you understand it a bit better. You probably won't need to be thinking about all these fulcrums and levers when you're working through the problems and when you're using the chain rule to differentiate, but I think it does at least give you a little bit of insight into why it works. So next we'll move on to a few examples.